Well, welcome back to lesson number 16 in our study of the transport layer of the TCP/IP model. For the last several lessons, we have been discussing flow control and congestion control. Given this overview of TCP congestion control, we're ready now to examine the details of the TCP congestion control algorithm. So let's get started. The algorithm has three major components: slow start, congestion avoidance, and fast recovery. Make a note of those. Slow start, congestion avoidance, and fast recovery. Slow start and congestion avoidance are mandatory components of TCP, differing in how they increase the size of cwnd in response to received acknowledgments. We'll see shortly that slow start increases the size of cwnd more rapidly than congestion avoidance. Fast recovery is recommended but not required for TCP senders. When a TCP connection begins, the value of cwnd is typically initialized to a small value of 1 maximum segment size, resulting in an initial sending rate of roughly maximum segment size divided by round trip time. For example, if the maximum segment size is 500 bytes and round trip time is 200 milliseconds, the resulting initial sending rate is only about 20 kilobytes per second. Since the available bandwidth to the TCP sender may be much larger than maximum segment size divided by round trip time, the TCP sender would like to find the amount of available bandwidth quickly. Therefore, in the slow start state, the value of cwnd begins at 1 maximum segment size and increases by 1 maximum segment size every time a transmitted segment is first acknowledged. TCP sends the first segment into the network and waits for an acknowledgment. When this acknowledgment arrives, the TCP sender increases the congestion window by 1 maximum segment size and sends out 2 maximum sized segments. These segments are then acknowledged, with the sender increasing the congestion window by 1 maximum segment size for each of the acknowledged segments, giving a congestion window now of 4 maximum segment sizes, and so on. This process results in a doubling of the sending rate every round trip time. So you see, the TCP send rate starts slow, but grows exponentially during the slow start phase. But when should this exponential growth end? Slow start provides several answers to this question. First, if there is a loss event, in other words congestion, indicated by a timeout, the TCP sender sets the value of cwnd back to 1 and begins that slow start process again. But first, it also sets the value of a second state variable, ss_thresh, which is shorthand for slow start threshold, to the last cwnd divided by 2. That's half of the value of the congestion window when the congestion was first detected. The second way in which slow start may end is directly tied to the value of this slow start threshold variable. Since slow start threshold is half the value of cwnd when congestion was last detected, it might be reckless to keep doubling cwnd when it reaches or surpasses the value of slow start threshold. Therefore, when the value of cwnd equals slow start threshold, ss_thresh, slow start ends and TCP transitions into congestion avoidance mode. As we'll soon see, TCP increases cwnd more cautiously when in congestion avoidance mode. The final way in which slow start can end is if 3 duplicate acknowledgments are detected, in which case TCP performs a fast retransmit and enters the fast recovery state. You remember what the 3 duplicate acknowledgments means. On entry to the congestion avoidance state, the value of cwnd is approximately half its value when congestion was last encountered. Therefore, rather than doubling the value of cwnd every round trip time, TCP adopts a more conservative approach and increases the value of cwnd by just a single maximum segment size for every round trip time. Round trip time, the amount of segments sent in one round trip. Not a maximum segment size for every segment acknowledged like it did in slow start. This can be accomplished in several ways. A common approach is for the TCP sender to increase cwnd by maximum segment size bytes whenever a new acknowledgement arrives. For example, if the maximum segment size is 1460 bytes and the window is 14,600 bytes, then 10 segments are being sent within that round trip time. And each arriving acknowledgement increases the congestion window size by 1/10 of a maximum segment size, and then the value of the congestion window will have increased by 1 maximum segment size after acknowledgments when all 10 segments have been received. But when should congestion avoidance's linear increase of 1 maximum segment size per round trip time end? TCP's congestion avoidance algorithm behaves the same when a timeout occurs. As in the case of slow start, the value of cwnd is set to 1 maximum segment size, and the value of the slow start threshold is updated to half the value of cwnd when the loss event occurred. Recall, however, that a loss event also can be triggered by a triple duplicate acknowledgement event. In this case, the network is continuing to deliver segments from sender to receiver as indicated by the receipt of duplicate acknowledgments. So TCP's behavior to this type of loss event should be less drastic than with a timeout indicated loss. TCP halves the value of cwnd, adding in 3 maximum segment sizes to account for the triple duplicate acknowledgments received, and records the value of SS thresh to be half the value of cwnd when the triple duplicate acknowledgments were received. The fast recovery state is then entered. In fast recovery, the value of cwnd is increased by 1 maximum segment size for every duplicate acknowledgement received for the missing segment that caused the TCP to enter the fast recovery state. Eventually, when an acknowledgement arrives for the missing segment, TCP enters the congestion avoidance state after deflating cwnd. If a timeout event occurs, fast recovery transitions to the slow start state after performing the same actions as in slow start and congestion avoidance. The value of cwnd is set to 1 maximum segment size, and the value of SS thresh is set to half the value of cwnd when the loss event occurred. Fast recovery is a recommended but not required component of TCP. It's interesting that an early version of TCP, known as TCP Tahoe, unconditionally cut its congestion window to 1 maximum segment size and entered the slow start phase after either a timeout indicated or a triple duplicate acknowledgement indicated loss event. The newer version of TCP, TCP Reno, incorporated fast recovery. Figure 3.53, as seen here, illustrates the evolution of TCP's congestion window for both Reno and Tahoe. In this figure, the threshold is initially set equal to 8 maximum segment sizes. For the first 8 transmission rounds, Tahoe and Reno take identical actions. The congestion window climbs exponentially fast during slow start and hits the threshold, SS thresh, at the 4th round of transmission. The congestion window then climbs linearly until a triple duplicate acknowledgement event occurs just after transmission round 8. Note that the congestion window is 12 times maximum segment size when this loss event occurs. The value of SS thresh is then set to 1/2 of cwnd, which would equal 6 times the maximum segment size. Under TCP Reno, the congestion window is set to cwnd equals 6 times maximum segment size and then grows linearly. Under TCP Tahoe, the congestion window is set to 1 maximum segment size and grows exponentially until it reaches the value of SS thresh, at which point it grows linearly. This slide presents the complete description of TCP's congestion control algorithms. Slow start, congestion avoidance, fast recovery. This figure also indicates where transmission of new segments or retransmitted segments can occur. Although it's important to distinguish between TCP error control, retransmission, and TCP congestion control, it's also important to appreciate how these two aspects of TCP are linked. We've now discussed slow start, congestion avoidance, and fast recovery. Ignoring the initial slow start period when a connection begins and assuming that losses are indicated by triple duplicate acknowledgments rather than timeouts, TCP's connection control consists of a linear or additive increase in cwnd of 1 maximum segment size per round trip, and then having a multiplicative decrease of cwnd on a triple duplicate acknowledge event. For this reason, TCP congestion control is often referred to as an additive increase, multiplicative decrease form of congestion control. AIMD congestion control gives rise to the sawtooth behavior shown here, which also illustrates TCP's probing for bandwidth. TCP linearly increases its congestion window size and therefore its transmission rate until a triple duplicate acknowledgement event occurs. It then decreases its window size by a factor of 2, but then again begins increasing it linearly, probing to see if there is additional available bandwidth. That concludes our sessions on flow control and congestion control in the transport model. So let's stop here. I think this has been a tough one. So take your time, go back over the videos, check your notes, gather your thoughts together, and make sure you understand these principles thoroughly. And we'll meet again at the next lesson.